Good afternoon, everybody, and welcome. It's my pleasure to welcome you here to this Gresham College lecture. My name is Roberto Trotta. I'm a professor of astrostatistics at Imperial College London, and I'm a visiting professor of cosmology here at Gresham College. And today, we are here to ask the question of what has Einstein ever done for us? Einstein, we all recognize him, is the iconic genius who has defined what it means to be a physics genius in the 20th century and beyond. Disheveled hair, head permanently in the stars, complicated ideas that only very few people can understand, or so we like to believe. And today we are here to actually learn that perhaps things are not quite as straightforward as this. Yes, complicated ideas, but very, very relevant for our everyday life. And our story begins in 1919, when Einstein, a few years earlier, made an astounding prediction, a prediction that contradicted everything we thought we knew about gravity. Einstein predicted that during a solar eclipse, we should be able to see stars around the rim of the sun in a position that is not quite what you would expect according to Newton's theory of gravity. And indeed, in November 1919, once the expedition led in May by Sir Arthur Eddington of the Royal Astronomical Society reported on the results, Einstein's ideas were on the front page of every newspaper around the globe. Essentially overnight, in one night, Einstein became the recognizable genius that we all remember and know about. So, for example, the New York Times led with lights all askew in the heavens, men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be by Newton, indeed exactly where they were calculated to be by Einstein, but nobody need worry. So it wasn't quite as scary as those headlines might make you think. So what was it that Einstein had predicted so successfully? What was it that he said in his book For 12 Wise Men, as the New York Times reported? And the crucial insight of Einstein's, that he published in 1915, was that space and time are not two separate entities like we experience them in everyday life. They're actually unified in a dynamic continuum which is malleable, changeable, respondent to the presence of mass and energy, which we call the space-time continuum. And so Einstein's masterstroke was that he put together space and time in one four-dimensional entity, and he said the space-time is not immutable, is not a grid, is not static, it's a dynamic entity which bends and changes shape in response to the presence of a mass. Like in this example you see here, if you place a heavy object like the Earth, for example, it will bend the shape of space-time. The moon goes around the Earth in an orbit. We think of it as a circular orbit because Newton told us there is something called gravity that keeps the moon on its circular orbit. Einstein says nothing of the sort. The moon is trying to go in as straight a path as it possibly can. Only a straight path in a bent space-time looks like a circle. Gravity is not a force. Gravity is geometry. And so if this is so, Einstein reasoned, if you put the sun in the middle of space-time, the shape of space-time will change, and light will also feel this distortion, despite the fact that we know light is massless, doesn't have a mass. So under Newtonian theory of gravity, there is no reason why light should feel gravity if gravity is a force that is exerted between two masses. Light is massless, but according to Einstein, still subject to the effect of the change space of space-time. So if you have light traveling through the cosmos, that light gets bent by the presence of the sun, and there is an angle here, a difference in the position where the star actually is behind the sun and the position in which the star appears on the sky if you just continue in a straight line. That angle here can be calculated, and Einstein did so, and he found that the angle under his theory of general relativity was twice as big as the angle that you would get using Newton's theory of gravity with a fudge, because like I said, you can't really compute this angle from first principle under Newton's theory of gravity. And so once Einstein verified, or Eddington verified Einstein's prediction of the existence of the bending of light, which in turn proved the idea that space-time is what Einstein said it was, then another series of ideas came forth, because now general relativity had enormous consequences for our understanding of gravity, astronomy, and the universe as a whole. One of them being the existence of black holes, which are depicted on this slide. I hope you can see the black hole at the center. Not quite? Well, it's here. There is one supermassive black hole, indeed, at the center of our own galaxy, the Milky Way. We can't really see it, not yet. We might be able to do so in the near future, but we can detect its presence through its gravitational effect. It is black, it doesn't emit light, or at least the black hole itself doesn't. The gas that falls into the black hole might and will. But the black hole is there, it's supermassive, and therefore exerts a gravitational pull on objects like stars going around it. So if we look at the orbit of stars near the galactic center, you can see, especially when we switch on adaptive optics to make the picture less blurry, you can see how they go around an invisible point here, or in this slightly more, perhaps more elaborated animation, you can see the orbit of these stars clearly going around a point which apparently, well, is empty, except that's where the black hole is. So Einstein didn't predict black holes, Friedman did, Einstein didn't predict black hole, but Schwarzschild did in 1916 as a consequence of Einstein's theory of general relativity. And indeed, those black holes, not only do they exist, not only can we see them because of their gravitational effect, as of last year, we can even image them. This is a famous picture that was again on all the newspapers around the world last year, showing a supermassive black hole in the M87 galaxy, some 53 million light years away. The black hole lurks somewhere here in the center. What you see here is the event horizon, i.e. this region of space out of which nothing, not even light, can escape. And this around here is the gas that feeds the black hole, that heats up as it falls into the black hole and therefore emits high energy light. So really Einstein made all sorts of different predictions, or rather opened the way for all sorts of new ideas that were then brought forward by others following his footsteps. Another key prediction that Einstein himself made in 1916 was that if space-time is an entity like Einstein said it was, it ought to be able to transmit waves. Those are special kind of waves, gravitational waves that are different from the sound waves that I'm using here to talk to you today, are different from the light waves that we're used to in the form of photons and visible light. Those are different kind of waves that perturb space-time in a very specific manner. You can see in this animation, space-time gets stretched in one direction and compressed in the other, and it pulsates like this. And so if those waves exist, like Einstein predicted they do in 1916, they propagate at the speed of light. And if you have a detector which is L-shaped, like this is the LIGO detector in Hanford, and you've got a laser beam going back and forth each of the arms of the detector for 4 kilometers. The laser beam then are reflected at the bottom of the detector, come back, and are reunited here at the center. If indeed a gravitational wave passes through the detector, what happens is this arm will get shorter, and this arm will get longer, and then vice versa as the wave passes through, and you ought to be able to measure the difference in length due to the stretching and compressing of space-time. Now that's a hard measurement. Over 4 kilometers, the difference in length induced by the gravitational waves is about 1/10,000th of the diameter of a proton. So that's small. That's why it took 100 years for physicists, engineers to put together the kind of detector that would be so insulated from every other disturbance as to be able to detect this tiny, tiny, tiny change. So space-time is very stiff. It doesn't really bend all that much. But, as you all know, it occurred. And it occurred in 2015, September 2015 for the first time, when the two detectors, one in Louisiana and one in the state of Washington, picked up the same signal, the same trembling and wiggling and quivering of space-time, which was brought about by the merger of two black holes that merged into a single black hole, and as they did so, about 3 times the mass of the sun was emitted in the form of gravitational waves energy, and that was a prompt Nobel Prize for Physics in 2017. So Einstein was right on that account as well. Here's a simulation of what a black hole would look like if you were unlucky enough to be very close, because you'd be sucked in and spaghettified. This is the event horizon. You can see around the black hole, the distortion of space-time induced a distortion of the background objects because the light coming around the black hole is so distorted that you get these fantastical shapes. And you also get multiple copies of the same object as the light gets split and then comes at you from different directions. And indeed, this kind of splitting of the light is observed not just in terms of the eclipse experiment that we just saw, but in cosmology as well, where we observe all sorts of beautiful instances of the space-time distortions predicted by Einstein. Here, an Einstein cross. These four objects are one and the same distant galaxy whose light is being split four ways by the intervening cluster of galaxies here. Here's another example of a beautiful Einstein cross. Here you see an Einstein ring, which is not quite complete, so it's one single object being distorted into the shape of the ring. It's called the horseshoe lens. And here, a very beautiful example of what is technically called a smiley face, I believe. And here, another beautiful example of Einstein arclets here, which are produced as the background light from these distant galaxies gets bent by these other yellow galaxies, which are clustered together in a gravitationally bound object, a very rich cluster of galaxies. And the beauty of this picture is that it allows us to estimate the mass of the cluster here by looking at how much bending it produces. That tells us about the total mass of those galaxies together, which far exceeds the mass that is visible in the picture or indeed in any other picture you could take with light. And that is one of the lines of evidence for the existence of dark matter in the cosmos. So you see, there is all sorts of different consequences to Einstein's ideas, including another one that was perhaps so mind-boggling that Einstein himself resisted the insight. The idea that the universe itself as a whole is dynamic and expanding over time, which was in the equations that Einstein wrote down in 1915. But Einstein didn't believe it. In 1915, remember, we didn't know there were other galaxies in the universe. We certainly didn't know the universe was expanding. The evidence for the expansion was gathered by Edwin Hubble in 1929, and on the back of theories that were produced, among others, by the Belgian priest and astronomer Georges Lemaitre. So in 1929, Hubble discovered the expansion of the universe, but Einstein in 1915, when he saw the possibility in his equations, he wasn't happy with that because he thought the universe was static, immutable, and eternal. So an expanding universe didn't fit with Einstein's worldview, so he put in an extra term. He wrote in an extra constant of nature that he called the cosmological constant in his equation, whose only job was to counterbalance gravity, so that Einstein's universe would be finely poised, just like a pencil on its tip. It can be made to stand on its tip, but the lightest perturbation will make it fall. So was Einstein's finely tuned universe, that he engineered to not expand, not contract, do not change with time. But then when Hubble uncontroversially and in a very powerful way showed through this graph showing the expansion velocity of galaxies as a function of distance that the universe is expanding, Einstein came to realize that this must be so, that the universe is expanding, and therefore, if you go back in time, it did start from a beginning, which Fred Hoyle memorably called the Big Bang at the time when he was opposed to the idea in the 1950s. And so Einstein in 1932 apparently recanted and said, oh, this was my greatest blunder. I should never have put it in, because indeed the universe does expand under the influence of gravity. So you see, we got all of these beautiful ideas, all of these fantastic consequences of Einstein's general relativity. And this is another one, the beginning of the universe, a picture of the very first 380,000 years of the universe as taken by the Planck spacecraft a couple of years ago, showing us what the universe looked like when it was in its infancy, very early on, at the time when Einstein's theory of gravity predicts the universe was much smaller, much hotter, and much simpler than it is today. All of this thanks to Einstein. We all know he is a great genius. We all know those are great, fantastic ideas, and we all suspect that they're all very far away or very irrelevant to our everyday life. Black holes, the Big Bang, deflection of light, dark matter, you name it. Those are fantastic insights, but why should we care? Surely those are too far away. Those are too extreme examples of physics to ever impact our everyday life, right? Well, actually, wrong. The astonishing fact is that those very same ideas that led to these incredible mind-blowing discoveries about the nature of the universe and indeed the nature of reality itself actually have very practical consequences for our everyday life, including the GPS system that many of us perhaps use to navigate and find our way here today to this lecture, nuclear power generation, wireless capabilities which we all use every day in our Wi-Fi devices. Even Instagram can be seen as the ultimate consequence of a daisy chain of discoveries that goes back all the way to Einstein. And one day in the future, perhaps even quantum computing might be one of Einstein's gifts. So let's go through them. And let's go back to the other giant of physics, Newton himself, and the story of the apple, which you will all have heard about. In 1666, Newton was apparently sitting under the apple tree in his garden in Lincolnshire when he was hit on the head or saw an apple falling, and that made him made him realize that the force that was attracting the apple was the same force that was attracting the moon, and therefore that was the beginning of his ideas around the universal laws of gravitation. Universal laws that, as we just saw, were an absolute revolution in physics, but are not quite the whole story. Einstein then took issue with universal laws of gravity, said gravity is not a force, it's actually the shape of space-time. And the reason of this difference is because Newton saw the universe as a clockwork universe. He saw the universe as a place where a ball is a ball everywhere in the universe, where there is a deterministic relationship between things, probabilities do not play a role, everything is subject to the same static laws. Space and time are two different dimensions, and therefore the universe is a clockwork universe in Newton's view. Not so in Einstein's view, who famously arrived at his theory of relativity by considering or imagining what the universe would look like if you were able to ride on a beam of light, and the speed of light being a constant of nature and the same for all observers being one of the cornerstones of special and then general relativity. So Einstein realized that if you look at the universe from the perspective of a beam of light, things are different. Newton's ideas about gravity, for example, have to fall by the wayside because they do not apply in the same way. So one of the key insights that Einstein had, or that led the way, in a sense, to the establishment of general relativity, is a piece of physics that we need to understand in some detail, and it's remarkably simple and remarkably powerful. It goes under the name of the equivalence principle. Now imagine a situation where you're in deep space, in a rocket. There are no windows and no other way of establishing actually where you are. So you're just closed in essentially in what could look like an elevator cabin. And the rocket has got thrusters, so it's accelerating upwards with an acceleration that matches the same acceleration that you get from gravity here on Earth. So if you let a mass go inside the rocket, well, because the rocket is moving upwards, accelerating upwards, to you inside the rocket, that mass will appear to fall downward with an acceleration given by g, small g. But now, if you are on the Earth and you are inside the same box and you let the mass go, obviously the mass will fall in exactly the same way. And the equivalence principle, Einstein says, is that if I'm inside that closed cabin, there is no possible experiment I can devise that will allow me to distinguish between these two situations. Here, the mass falls because of the accelerated motion of the rocket, no gravity involved. Here, the mass falls because of the force, quote unquote, of gravity on Earth. There is no way of distinguishing between the two. The acceleration due to gravity is indistinguishable from the acceleration due to any other force. So that's all very well, but now let's do a slightly different experiment. Let's use a light beam instead. And our experiment is going to be to shoot the light beam horizontally across the rocket as the rocket moves upwards. Now, because the rocket moves upwards, if I'm inside the rocket, the beam will appear to curve downwards for me as an observer as it traverses the moving rocket. But by the equivalence principle, Einstein said, the same must be true in the presence of a gravitational field. Because if that wasn't the case, then by doing this experiment, I would be able to distinguish the two situations, which I'm not allowed to because of the equivalence principle. Hence, the presence of mass, gravity must bend light, which is what we saw before, the key insight that allowed Einstein to make his prediction about the bending of light during the solar eclipse. And it's all due to the equivalence principle, a very simple yet powerful idea at the very basis of relativity. Now let's do a slightly different experiment and let's explore the further physical consequences of the equivalence principle. Now we are in deep space in our rocket, and the rocket is accelerating upwards, and as it does so, we're going to shoot a light beam, again, working with light, from the bottom of the rocket. So we're going to shoot it here, and then we're going to detect it at the top here. Now, because as the light beam moves upwards, the rocket is also accelerating upwards, by the time the light beam reaches the ceiling of the rocket, the ceiling will have moved away, which therefore, from the point of view of a detector placed in the ceiling, means the wavelength of light will have been stretched. So if the wavelength of light has been stretched, that means that the frequency of light will be longer. The light beam will be a little bit redder in that situation. So if I now define a second by the number of crests of that light that pass me by, now I shoot the light beam off, and I count 1 second, let's say 10 oscillations of the light beam. By the time the light beam is at the top, my 1 second, the time that it takes for me to count these 10 oscillations, because the frequency has now increased, that time the frequency has decreased, that time has also increased. In other words, in order to count 10 oscillations at the top, I need to wait a little bit longer, because the frequency of the beam has been decreased and the light wave has been stretched by the fact that it's moved upwards in the accelerating rocket. Therefore, what I conclude is that the delta t, the difference in time between the first wave and the last wave at the top, is a little bit longer, i.e. time at the top, if I have a clock at the top of the rocket, has passed a little bit faster. Time is not a clockwork. Clocks run in a different way depending on their state of motion. Another key insight of relativity. But by the same token, using the equivalence principle, the same must be true in the gravitational field as well. So if I do the same experiment here, I must make the same observation at the top. Otherwise, I would be able to distinguish between the two situations, and I'm not allowed to. Therefore, Einstein concludes, time at the top goes a little bit faster, and time at the bottom flows more slowly. So if you're in the vicinity of a massive object, because of the gravitational time dilation, time flows more slowly in the vicinity of a mass. And so that might not appear like much, but depending on what mass you take, it adds up. So a year on the surface of the Earth corresponds, if you were on the surface of the Sun, to a year minus a minute and a half. So time is slower on the surface of the Sun. And if you go on the surface of a neutron star, where gravity is so much stronger, and again, I use sort of Newtonian terms to describe it, although we now know that we should really say where the bending of space-time is so much more extreme, well, then in a year, you gain a day and a half. And indeed, the effect is small, but measurable on the surface of the Earth. If you're at sea level and you clock a second, you go to the top of the Everest, that 1 second corresponds to 1.00008 seconds. So time is a little bit faster at the top of the Everest, which is why I always recommend go to the sea for your holidays. They will last longer. So this is tiny. Again, you think, well, sure, why do we care? Well, it's tiny, but importantly so. It's not beyond the realm that we need to actually consider it in applications such as GPS, the global positioning system that is used by all of our navigational devices today. It's a fleet of satellites which orbit the Earth twice a day, 20,000 kilometers up. At 20,000 kilometers up, the curvature of space-time is a quarter what it is here. And therefore, now this effect becomes important, because the way your devices work, they triangulate the signals coming from at least 4 satellites at the same time to give you a fix, to give you a position in 3 space coordinate and time on the surface of the Earth. And we all know it works beautifully, but it wouldn't work beautifully. In fact, it would not work at all if it wasn't for Einstein. Because those satellites, first of all, they travel at relatively high speed. So the clocks on those satellites, the time for them flows differently because of special relativity. And so over a day, there is a correction of 7 microseconds due to special relativity. But there is a much bigger correction of 45 microseconds a day because of the time difference due to the difference in flowing of time at that altitude with respect to time here on the surface of the Earth. And if you add them up together, it gives you a relatively large difference in time of 38 microseconds a day, which, if not corrected for, would mean that after a day, your GPS would be off by 10 kilometers. Or, put it another way, if you want to use it to stay on the road and know where you're going, let's say that the road is 10 meters wide, without Einstein, your GPS would lead you astray after 2 minutes. So that's pretty important. So Einstein really is helping us in every time we use those devices. But Einstein is helping us in other interesting and perhaps unexpected, surprising ways. The theory of general relativity was published in 1915. Schwarzschild in 1916 then took the equations and showed that they led to the prediction of the existence of those punctures of space-time that we call black holes, which we saw the evidence for a little while ago. Stephen Hawking in 1974 then realized that black holes are not entirely black. Actually, he realized by combining general relativity and quantum mechanics that black holes must emit some form of energy, in fact. So black holes are actually really gray. They do so over a very long time scale, so it has been impossible, it might forever be impossible to actually detect that Hawking radiation, the evaporation of black holes that Hawking predicted in 1974. Nevertheless, in 1992, John O'Sullivan, a radio engineer in Australia, was working on a radio telescope to try and devise a way to detect this kind of Hawking radiation from radio emissions from black holes. Now, he didn't do that, but what he did is stumbled on an algorithm that he was trying to develop in order to clean the signals that he was getting from the radio telescope looking for the Hawking radiation. And he realized that that algorithm was very powerful in cleaning out radio signals, especially in circumstances like in this building where there are multiple reflections and there's lots of interference, lots of noise. And then he patented it, and it became the cornerstone of what is now the Wi-Fi chips inside our phones and laptops and so on. So billions of users nowadays have reliable, fast Wi-Fi because of Einstein. That's perhaps the most iconic formula ever, E equal mc squared. It's on every T-shirt, of course, and Einstein is remembered for it. And it's at the heart of the nuclear fusion that goes on at the center of the sun. The fact that we can convert energy into mass and vice versa, and the speed of light, c, is a conversion factor, means that if you are able to just convert a tiny little bit of mass, it will, because c is so large, you'll get a lot of energy, which is, of course, the principle behind nuclear power generation through fission presently, but hopefully through fusion in the near future. So we can split the atom and convert a massive atom into 2 smaller atoms and get some energy out of it. Of course, the price we pay is the problem of radioactive fissile material that we need to store for a very long time. In the future, we might be able to do the reverse, take 2 light atoms like hydrogen and helium, which are essentially the fuel that the sun uses for its fusion processes, and get effectively unlimited energy for humanity forever if we are able to master those fusion processes in the lab. That is one of the main aims of the ITER project, a European-wide fusion reactor project that is set to try and achieve and sustain stable fusion in the next power generation in the next 10 to 15 years. And if that were to happen, of course, there would be a major, major change of direction for humankind, and especially in the midst of the climate emergency we are facing. Unfortunately, the negative side and the scary side of that is nuclear weapons, which are also a consequence of this formula. Einstein was very, very concerned, and he wrote to President Roosevelt expressing his concern at the beginning of the war. when he realized that indeed these ideas could be used to create a weapon of incredible power, destructive power. And so he was perhaps in a way instrumental into setting up the Manhattan Project that eventually led to the American bomb. Later, Einstein realized that perhaps he had overreacted, or rather he had been misguided in his thinking. He was concerned about the Germans getting the atomic bomb. And later, he was a staunch pacifist, and he tirelessly campaigned for the abolition of nuclear weapons. And he also said that had he known that the Germans would not succeed in developing the atomic bomb, he would not have done anything to facilitate or to spur on the Manhattan Project. Here's another consequence of Einstein's idea, actually the idea for which he got the Nobel Prize for Physics in 1921. Einstein did not win the Nobel Prize for his revolutionary ideas about space and time, for interesting historical reasons that might be material for another time. He did, however, win the Nobel Prize for his equally revolutionary ideas about the photoelectric effect. The photoelectric effect is something that puzzled physicists a great deal at the turning of the last century. So thinking now of light, as people did at the time, as a wave, then the frequency of light corresponds to different colors and different energies. So a longer wavelength corresponds to low energy, while a faster wavelength corresponds to high energy, red towards blue. And so the physicists had known for a long time that if you shone a beam of light on a piece of metal, you could get a current to flow, but only under certain circumstances. So for example, if you shone a beam of red light onto a piece of metal, you would not get any current. No electrons would be freed from their atomic embrace in the nuclei, and you would not get an electric power. No matter how long you shine the light on the piece of metal, nor what the intensity of the light is, you simply cannot get any current to flow. If you wait for longer, nothing happens. If you shine a slightly higher energetic beam of light, say green light, still no electrons until you get to sufficiently energetic beam of light, say blue, in which case you do free some electrons, negative charge particles, which make up the current. And so understanding why this was the case, that you would not get an electric current out of these pieces of metal under any circumstances unless the wavelength of light was above a certain threshold, was a big puzzle of physics around the turning of the 19th to 20th century. Nobody could understand it because, after all, yes, there is less light in red, there's less energy in red light, but if you keep shining this light for longer, eventually you'll accumulate enough energy, so people thought that the electrons should be freed. But Einstein realized this was actually the tip of an iceberg, that if you could understand and explain this, an entire new vista of physics would open up. He realized that the reason why this light couldn't free up the electron was that light was not exclusively a wave, but you can think of light as a particle, too, at the same time as a wave. And so if light is a particle, and as a particle it contains and carries a certain discrete amount of energy, it's quantized, as we now say, then red light simply had packets of energy that were insufficiently energetic to free up the electrons, to kick them off their orbits. There simply was not enough energy, and you could not deliver enough of a punch in one packet of light in those circumstances. But when you go to higher energy, bluer light, then that light packs more energy into a quantum, and that was sufficient to kick off those electrons away from the orbits and the current flow. This is the photoelectric effect, and Einstein explained it in terms of the new and fledgling theory of quantum mechanics. Now, why is this important? Because this is the principle behind all of the digital cameras that we now carry with us everywhere that have replaced film. The fact that this digital camera can convert light into a current goes back to this very first principle. And so Instagram would not exist today unless Einstein had, if it wasn't for Einstein's ideas about how to understand this phenomenon, which eventually led to the development of CCD cameras in our devices. And so finally, to look at the future, to what we might expect in the future from Einstein's ideas, we need to delve a little bit further into the frankly crazy world of quantum mechanics. So moving away from cosmology, from the infinitesimally large, going to the very, very small. And this idea that I mentioned before, that waves, light is a wave, but also a particle at the same time, and the same is true for every other particles that we can think of, which goes by the name of quantum duality, something that Einstein himself was very uncomfortable with. He never liked nor really believed in quantum mechanics. But let's explore this a little bit further. So there's an experiment that you can make with light. You can shine light in the form of, think of it as waves. Shine light through a double slit like this, where you have two passages, one here, one there. As the light fronts hit the double slits, they get reshaped into one source here, one source there. And just like, if you imagine this being waves in a pond, those waves propagate past the slit, and where a crest of the wave meets a trough of the wave, they'll interfere and they will cancel each other. And when two crests meet, they will add on top of each other. And so if you shine that light onto a screen, what you see is a pattern like this, where you get light, 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 and then darkness in between. It's called an interference pattern. It's just waves on top of each other, which is an experiment you can make with lasers, for example, and that tells you that obviously light is a wave, surely, because it behaves just like you would expect a wave to behave, interference of waves. But then let's do a slightly different experiment. Let's put a camera here looking at one of the two slits. So the camera will click if and only if a particle passes through that slit. Now, of course, we think of light as wave, but Einstein told us with a photoelectric effect that it can also be seen, indeed it must be seen, as a particle. And so if you now change the experiment and we put a camera in, something incredible happens. The interference pattern disappears, and all you can see is two spots of light, one corresponding to particles going through this slit, and one corresponding to particles going through that slit. The fact that we now have an experiment in place that tells you which of the two routes light took, if it were a particle, forces it to behave as a particle. Light is a wave and a particle at the same time, and what you observe, the way it behaves, depends on how you set up your experiment. It gets even crazier. You can do this by making the choice of whether or not to activate or put in the camera after the light has passed through the slit. And still it works, as if light knew it in advance. Really crazy, really crazy. Einstein himself thought it crazy. But it works. We can use this crazy theory of quantum mechanics to predict all sorts of phenomena with uncanny precision. So clearly quantum mechanics works, even though we don't really understand it. In terms of ontology, what is the reality of the quantum world is an open question today in physics. And it works also for things that we believe are particles, like electrons. We think of electrons as little particles, little points of charge, perhaps. And you can shoot electrons through a double slit experiment just like this one, and surely you think they will behave as particles if they are particles. You can shoot them one at a time, and you can see that's a screen at the bottom. You can see the electrons hitting the screen one at a time, independently from each other, and if you run the experiment for long enough, all these electrons who travel through the double slit independently from each other at different times from each other, eventually they all build up an interference pattern, just like as if they were waves. So we must accept it. We may not understand it, but we must accept it. Quantum mechanics describes the world in indeed very strange terms. But Einstein wasn't comfortable with this. He hated it. He fought hard all of his life to find the completion of quantum mechanics, a way to understand it that would make sense, that you could make sense. And in an effort to do that, he, together with Podolsky and Rosa in 1935, devised a thought experiment. And he said, all right, let's assume quantum mechanics is as crazy as it appears. Let's take two quantum mechanical particles, and let's put them in a quantum superposition state, i.e., they are a little bit yellow and a little bit blue at the same time, just like the particles we saw before can be thought of being a wave and a particle at the same time. And then we're going to set them up in such a way that those are twin particles. They're set up exactly in the same way, and we're going to send them a great distance apart to the opposite corners of the universe. It's a thought experiment. We don't actually need to do it, just to think about it. And then one of the two observers, somebody here, will make an experiment that will determine whether the particle is yellow or blue. Like so. Let's say that they find it's yellow. Therefore, quantum mechanics predicts that when I make my measurement here in this galaxy, the other particle, the twin particle at the other end of the universe, if necessary, will immediately turn the same color, or the opposite, depending how you set up the experiment. But it's deterministic. It happens. And it happens with no time delay. A complete violation, apparently, of causality. Spooky action at a distance, as Einstein put it in 1947. So he said, surely that's not possible. Surely that violates relativity. Surely that shows quantum mechanics is wrong. Well, on this one, Einstein was wrong. Because in the 1960s, a series of experiments were made, not of this kind, but based on this idea, that did show that this is exactly what happens. Relativity and causality are actually saved in the same token, because yes, it is instantaneous, but it doesn't carry information. So you cannot use that to carry information faster than light. So causality is saved. So why is this important? Well, first of all, because it shows how crazy quantum mechanics really is, but also because we might be able to use it in the near future to build a quantum computer. Now, computers, the ones that we now have and have had for a number of years and are now powering the machine learning revolution in science and society, work with bits of information which are essentially, if you can think of it as little parcels of information that can take only two values, 0 or 1. So if I have 2 bits in a classical computer, I can have 4 different possibilities. Either they're both 0, both 1, or 1 is 0 and the other is 1, or vice versa. And so a typical computer will work with classical 0 or 1's bits. A quantum computer, though, based on the ideas that Einstein fought so hard against, but nevertheless were proven right, is able, because of the characteristics of quantum mechanics, not just to have zeros and ones, but to work with all the numbers along the cycle, an infinite number of possibilities, all at the same time. Quantum computers do not need to decide. They can work with all of these possibilities simultaneously, which means that our typical classical computers have 64 bits today, and that means that in any given time that can represent one state out of this number of possible combinations. But a quantum computer, like the ones that are being currently developed, and some say have already reached quantum supremacy, although this is a controversial claim at the moment, i.e. the ability to carry out calculations much faster than conventional computers, while those quantum computers using qubits have a much smaller number of states, but they can explore them all at the same time, simultaneously, using the quantum properties that we talked about. And they have the ability of taking some of the calculations that are essentially impossible for a traditional computer and make them instantaneous or very, very fast indeed. So that might be yet another gift that Einstein's ideas, in this case ideas that he fought against but that he helped establish, might give us in the near future. And so, like I said, Einstein was very skeptical of quantum theory. He did say that quantum theory yields much. He was convinced of that, but it hardly brings us close to the old one's secrets. I, in any case, am convinced that he does not play dice with the universe. He wrote to another of the founding fathers of quantum mechanics, born in 1926. But on this one, like I say, old Einstein was wrong, and apparently quantum mechanics does play dice with us, and pretty well as well. And so it's been quite a journey. We've gone from the Big Bang to black holes to Wi-Fi, and perhaps to the future of quantum computing. I hope that I've been able to convince you that Einstein's ideas, as beautiful as they are, as inspiring as they are for our knowledge of the universe and the nature of reality around us, they're not only that, they're very practical, they're very useful, they've changed our lives. So next time that you ask, what has Einstein ever done for me? Well, take out your phone, have a look. That is what Einstein has done for you. Thank you.